So if I get asked to implement this 2-bit comparator in SystemVerilog, well, there's a couple of things that I can do. First, I see that there's two XNOR gates here, and their output goes into the single AND gate here. Well, I could draw out the whole truth table, but I'd have to include all possible combinations with these 4 bits. So all possible combinations of 4 bits is actually 16 combinations. It's a lot of combinations, but certainly not impossible to do. Then I would have to make a K-map, and I can create an expression which comes out to be an expression for the output, and this comes out to be a function of A0, B0, A1, and B1, just like that. The other better option that I can do is I can inherit from the previously made code and use it to my advantage, and I'll save time. If we remember in the last video, I made a comparator, or otherwise known as a XNOR gate. So let me bring it up here, and this was the truth table that came with it. Additionally, we could still figure out what to expect as an output depending on the input for this 2-bit comparator. Okay, so I drew this truth table here on the right for the comparator. So if we look at the XNOR gate here, we'll notice that you get 1 in the output only when both inputs are the same. So using this logic, we arrive to this truth table here on the right. Additionally, we can say that all other combinations here are going to produce a 0 in the output. Well, why is that? Well, since we know that the inputs for the individual XNOR gates have to be the same, we can look at them as pairs. So 0, 0, 0, 0 produce a 1 in the output. And then 0, 0, this result itself produces a 1 in the output of that specific XNOR gate, as well as these two. So that produces a 1. And then, you continue with that logic, and then you'll arrive to the conclusion that all other combinations must produce a 0. Okay, so here we are in model sim. So now what we have to do is we have to implement a new module that will inherit from EQ1 here. So I'm going to go to add to project, new file. I want to add it in my source folder. I go all the way to the right. So this file, we're going to call it EQ2. And the language is, of course, going to be SystemVerilog. We press OK. At the same time, we're going to add another file. And of course, you guessed it, it's going to be the Testbench. Let's go ahead and add that. So this is going to be EQ2 underscore Testbench. Language SystemVerilog. Okay, so now we have our 4 files here, and we can then start coding. So I'm going to go to EQ2. So here I am, and we're going to start like always. This module is named EQ2 after the file name, of course. So let's go ahead and declare our input and output variables. So input logic. So this time around, we're going to be using 2-bit variables for our input. So A is 2 bits and B is 2 bits as well. Output logic. And then my output, I'm going to call it AQB. So we're moving along. We're going to declare some internal variables here. So I'm going to call it logic E0 and E1. So in fact, these variables, if we look at my drawing here, they're going to be these two numbers here, or these two pins. This is E0, and this is E1. So that's where that's where these values are, or these variables. So let's continue here. So now what I want to do is I want to instantiate EQ1, which I had made previously. Okay, so now we actually perform the instantiation. So I'm going to call EQ1, and this object, I'm going to call it bit0 unit, in parentheses, dot I0, parentheses A, element 0, close parentheses, comma, I1, element 1, close parentheses, comma, and then we have EQ, E0, close parentheses. And then we instantiate the other one, EQ1, once again. So we say EQ underscore bit1. And you can name it whatever you want, but I choose to name it like this, because I'm following this textbook, but I'm making small modifications so that it's more easily understandable here. And then we want, this is actually going to be B. Then this is 1. And then finally EQ, E1. So here we can make a couple of remarks. We see that A corresponds to the first instantiation, B corresponds to the second instantiation, E0 corresponds to the first instantiation, so this is the output of the first instantiation, and then E1 is the output of the second instantiation. Furthermore, I0 and I1, we can reference them from EQ1 itself, so we see that the input for these values are I0 and I1, and then the output is EQ, so that's where these variables come from, I0, I1, and EQ. So the last bit of coding that we need to do is actually very, very simple. So now we just assign a value to the output, or assign an expression to the output. So I'm going to call it, if we look at the graph here, there's going to be an AND gate. So really, it's as simple as saying E0 and E1. Let me close that. And that does it for EQ2. Okay, so now we save our code here, and we move on to the test bench here. So I'm gonna start writing out stuff. So we want the timescale to be in units of nanoseconds, and time step is going to be in 10 picoseconds. Now we begin our module here. We're going to call it EQ2 underscore testbench, and that is of course after the name of the file. Then we can begin to declare some variables. Once again, we're going to be using a 2-bit variables. I'm going to call it test underscore in0, and the other one is going to be called test underscore in1. I'm going to set them initially to 0. Moving on, I'm going to declare another logic variable. The logic simply means that it's going to be a binary number. 1-bit binary number, of course. And we move on. So at this point, we can now instantiate the circuit under test. So we call it EQ2. This is also considered instantiation, but I don't count it because it's the test bench and you need to have this in order to test your code. Let's go ahead and write this out. And then B, like that. And then AEQB. And that's going to be in the test out. Now we're gonna give some values to the test inputs. So I'm going to say initial begin. I'm going to copy this from the code that I previously did. So here we can see that setting test input 0 to 2-bit number, and then I assign it 0, 0, and this is going to be the input for the A logic gate. The A logic gate, and then this is the input for the B logic gate. So if you look back at our diagram, this is going to be the A, and then this is the B. Okay, so I took the liberty to add all possible combinations. So in here, there are 16 possible combinations for these two values. That is the test input 0 and then test input 1. So after this now I have to stop the initial begin. And that should do it. So now we're ready to compile and test. Okay, so now I'm going to see if I can compile it. I had a couple of errors here. I misspelled initial and I was missing a semicolon here. Now I should be able to compile this. Go ahead. I have one error here. EQ2. Oh, it's going to be this semicolon. I don't need it here. So let's take it out. Save it. File. And there it is. All compiled. So now we can move on to simulating. So let's clear this out. Okay, so I'm going to go ahead and simulate. Restart simulation. And then this time around, I want to select EQ2 test bench. And then I press OK. This window is kind of weird. So now I want to use, let me open the objects window like that. This should be, why is it like that? Anyways, so I'm going to choose to look at my test inputs once again. So these two are going to be inputs, and this is determined by the test bench, and then the output is determined by the code itself. I can add that to the waveforms. So let me fix some of this here. I want more real estate for my waveforms. Like that. Okay, and then since it's already simulated, I can just run it. So it runs the code and it stops right here. So it actually ran through all of these combinations. So if you go back to the waves, I want to go to zoom full. Okay, so now we can begin to look at these waveforms. If we have our cursor here, we see that right? Input 0 and input 1 are both 0, 0. Therefore, I get a 1 in the output. We move along. We have a 1, 1, and then 0, 0, and then a 1 in the output. So that makes sense. And then here we don't have anything in the output until we get to this one here, which is 0, 0, 1, 1, and then we get a 1 in the output. That's good. And then we move along here till the very end. The very end has 1, 1, 1, 1, and that will obviously give us a 1 in the output. So let's take a look at what we expect to see in our this table here. So we saw that 0, 0 and 0, 0 gave us 1. We also saw this one. Also saw this one. And then the last one we saw was this. So then it is 1 for only 4 of the combinations. So if we go back here, we see that we have a 1 in the output 4 times, right? So that's 1 here, 2, 3, and then 4. So to summarize what we did, we instantiated 2 1-bit comparators right here, and that produced a 2-bit comparator. So this file, this module, EQ2, only needed a small line to assign a value to, or to assign an expression to AEQB, which is this expression here. So this is enough to implement the 2-bit comparator that we were looking at earlier, which is this one here.